Good morning, everyone. We welcome you all to the third lecture for this workshop. The first lecture for the day would be covered by Professor Geeta Venkataraman. We would be studying about Burnside's lemma and counting problems and Cauchy's theorem. Ma'am, we welcome you, ma'am.
Thank you. Should I start?
Yes, ma'am, please.
Yeah. So good morning to everybody. I wanted to first find out if any of you have doubts from yesterday's lectures, and in which case I'll clear that before I move forward. I hope you all enjoyed the tutorial sessions as well. You should have got a better understanding of what we were doing through them. Okay, so I will start. Let me share my screen.
Yeah, actually, I don't have a doubt, but just want to ask something.
Sure.
So, ma'am, when we were doing the examples of this group action, so
Yeah.
in one of them, we just took G to be the set of permutations.
Hmm.
And in the next one, when we took X to be square, and then we said we'll represent X by the 4 vertices.
Hmm.
And then we took G to be the dihedral group, that is D4. So
Correct.
basically, we are just taking the subgroup of the set of permutations there.
Yeah. See, so the way I defined your, so when X was sort of had some kind of, it was sitting inside R square or R cubed, then when I defined its group of symmetries, by definition, it was first a permutation on X, and additionally, it preserved distance. So in the way I've defined sim X, it's always going to be a subgroup of Sx. So D4, I mean, technically D4 is, you have to, the X that we are looking at is the entire square.
Yeah.
But it's enough to track the data of what happens on the 4 vertices. So in a sense, I mean, so which is why you tend to then think of D4 as a subgroup of S4. But I mean, technically, if I look, D4 is actually a subgroup of the rigid motions of the plane. If you remember what Amit did in his lecture yesterday, he showed that if you look at all the isometries of the plane, they form a group of rigid motions. So actually, when we are looking at any two-dimensional figure lying in the plane and considering its symmetries, they're nothing but the symmetries of the plane which take that object back to itself. So in fact, I think maybe today in today's lecture, he might be discussing these things, right? So I mean, so at one level, the dihedral groups are all going to be sitting inside groups of isometry or groups of rigid motion. But as far as we are concerned, because we are thinking of, in a way, saying that let's just restrict the action to those 4 points, which are the vertices of the square. And, whatever happens to the vertices clearly determines what happens to the square. And so it's a kind of, it's what's called representation. So instead of looking at G as a, I mean, the D4 as a subgroup of the group of isometries, I'm instead looking at it as a subgroup sitting inside S4. Yeah. So that action then, because I've named the vertices 1, 2, 3, 4, then the action of D4 on the vertices is the same as, well, I mean, it's restricted action of S4 on the numbers 1, 2, 3, 4.
Correct.
It's like that. In fact, that's one thing that I wanted to mention, that if the group G acts on a set X, and you take any subgroup of G, it will also obviously act on X. And in fact, I think in the tutorial sheet, in the first tutorial sheet, I had asked you to look at subgroups of, I think, S3.
Yes, ma'am. Cyclic subgroups that we
S3. And then look at the actions of those subgroups, because um, if you look at the entire Sn, it acts transitively on 1, 2, 3 up to n. And then I wanted you to, when you work with subgroups, you'll realize that some of those actions are not transitive. That was the main aim there. Okay, so shall I get started?
Yeah, ma'am. But as Cayley's theorem says that every group is isomorphic to some permutation group. So
Yeah.
when we study so many group actions, it actually boils down to some group action of a permutation group only.
Yeah, so see, the thing is that the reason why you want to think of groups as as subgroups of the permutation group, or also, you would at times like to take it into the general linear group. The reason is precisely because you can say a lot about permutations, which you cannot say about elements of an abstract group, right? So in an abstract group, suppose you don't know and I give you two elements, you're not going to be able to tell me whether those two elements are equal, what kind of an order that element might have even in a finite group, and so on. Whereas if I tell you that these are two permutations acting on a set of n numbers, then you can check whether they behave identically on all those n numbers, and if they do, then they're equal, right? And you can also find out so much more about them when you know that they're sitting inside permutation groups. So similarly, when you're looking at groups sitting inside matrix groups, the general linear group and so on, you get a lot of information, because the general linear group is, I haven't done that, and maybe Amit will talk to you about some of it, but you can think of the elements of the general linear group as acting on a vector space. So
Oh.
if you take the general linear group of degree n over a field f, then you look at an n-dimensional vector space over the field f, the elements, the matrices in that are acting on those vectors. So again, you can say a lot about the matrices themselves by looking at what they're doing on the vectors. So typically, when you're doing, um, when you want to do a lot of things with groups, one technique is to take to find some suitable action of the group, which will lead you to looking at it as permutations or looking at it as as matrices, because that gives you a lot more structure and tools which you can use to prove various things about the group. And this comes under an area called representation theory.
Yeah.
So that's something that this thing. So yeah, of course, it's true that through Cayley's theorem, you know that every group is a group of permutations. But at the same time, that's not enough sometimes to give you, because if you don't know the group that you're starting out with, and all you know is that it's acting on itself by left multiplication, and that gives you a homomorphism from G into Sx, which is X is also G here. It's not quite enough, because you really don't know much about G even as a set.
Mm-hmm.
So instead, you look for other types of actions which might help you get to smaller. And if G is large, Sx is going to be very huge. So you may not be able to utilize that information very well.
Mm-hmm.
So it's you're always looking for nice actions which will. So for example, one of the examples that I gave you, which is cosets of a subgroup,
Mm-hmm.
right? The group group acts on the cosets of a subgroup by left multiplication. That action often is extremely useful, because if within your group you know that there is a subgroup, say, which is quite large, so its index will be small, then really what you're doing is that you are going to get some information about your group G, because a quotient of the group G is going to be sitting inside that SM, where M is quite small. So these are all things which will give you more information and different tools to prove things. Yeah, so it's always very useful to find good actions.
Yeah.
But those actions will come from what you want to achieve, right? Um, and I mean, that's something that you should be looking for all the time. When you think of a group, ideally you should be thinking of it as acting on something, and that giving you a lot more information about the group.
Yeah, because earlier we were so used to that we are given a group and then we have to associate it to a permutation group. But when the group action things, like, it's for me, it's like a second Gita ka book. Like, you have to think it like a second adhyaya of the Gita. Like, you have to take it as you mentioned.
Actually, when we were taught group theory, it was from Herstein's book. That's not followed any longer. I mean, but it's a very good, I mean, it was a fantastic book, Topics in Algebra. But the entire book is written from a pure abstract group theory point of view, or of course it contains rings and vector spaces as well. So in that, you don't even think of a group as a group of, as a group acting on something. It's every result there is done purely algebraically through induction or something or the other, and there's no sense of a group acting on a set. And then when I went for my further studies, I realized that the first thing they're doing there with their undergraduates is to talk about a group acting on a set, and everything comes out of that. So it was quite a this thing, and you realize the powerfulness of getting a group to act on a set. And you'll see that. I mean, in fact, I'm not really covering that in the set of lectures here. But the moment you've proved just your orbit stabilizer theorem, and the fact that, the orbits form a partition, the distinct orbits form a partition of the set X, that just those two results actually you can prove, your Celos theorems, Cauchy's theorem, class equation, everything from just different actions. So anyway, let me get started on today's thing. Otherwise, we will run out of time at some point.
That's why I was thinking why the group actions are useful, and that's why I asked this.
Yeah. No, perfectly fine. I mean, so it's like, see, instead of proving results about each separate group, we study groups in abstract, prove things about groups in abstract, and that applies on all the examples that we have. In the same way, when we do group actions and the theory of group actions in general, by choosing specific actions, the same basic result that we've proved about group actions applied to that particular action gives us a theorem in group theory. So it's like a meta result or a meta theorem that you're proving. And then when you're applying it in various different cases, each is giving you a named theorem in a sense. Like Cayley's theorem is also coming out of group actions. And we'll see today, hopefully we'll get to it. And I'll be able to do Cauchy's theorem with you through a group action proof. Okay. And you'll see how it comes out so naturally. And that last question that I'd given in the tutorial sheet, that actually is the starting of a proof for Celos theorems. The aim is that you get, I mean, I think most students wouldn't have done that, but if you have a group G and a finite group G, and you have a prime P such that P to the power alpha divides the order of G, then what you have is a partial converse of Lagrange's theorem, which is, I mean, it's called Celos theorem. It basically tells you that the group will have a subgroup of order P to the power alpha. So the method of that particular group action is that you collect together all the subsets of order P to the power alpha, get the group to act on it, and through that find out that at least one of those subsets has to be a subgroup. So that's the logic behind that thing. I mean, it can be taken further and you can use it to prove that the group G will have a subgroup of order P to the power alpha. Okay, so
I'm
let's
sorry, I'm taking time. Just last question.
sure, sure.
Ma'am, is it always possible to find a action other than the trivial actions? Like if given any arbitrary set X.
Uh, I mean, you can always create.
Because if that won't be possible, then how we will
See, so the point is that um, you recall that if you have a group action, you're going to get a homomorphism from the group into Sx, right?
correct.
The so the thing is that it depends. I mean, for example, if I take a set which has three elements and my group is of order 8, say, okay, whatever action I have of the group G on this set of three elements, I'm going to get a homomorphism from a group of order 8 into S3.
Correct. Correct.
And then, I mean, so if I choose my group, say of, forget 8, if I take it of group of order 17, for example, then I have no choice but that the kernel will be the whole group. Which means that what I'm going to get is only a trivial action.
Yeah, yeah.
So the point is that it's not so much that you will, of course, you'll always have the trivial action. It's not always going to be possible. You're not really trying to find all possible actions. That's not what you're going to do. What you're going to do is that because you want to explore some aspect of your group or something else, you'll think of what might be a suitable action which will give you that.
Explore the group.
Okay, sometimes there are very natural actions which come automatically, but other times it's so like in the Celos subgroup, the proof of Celos theorem that I was talking to you about. The way the person would have thought about that proof is that, thinking that, okay, I have a subgroup of order P to the power alpha. I know Celos theorems are there already, right? And so can I figure out some nice action on subsets of order P to the power alpha, which then gives me through that there is at least one subgroup of order P to the power alpha, right? So it's with a purpose that sometimes you find the action.
Yes, ma'am.
Like if you want to prove that some all Celos subgroups are conjugate, right? So then you'll get G to act on the set of all Celos subgroups. Once you proved that there are Celos subgroups, you get it to act on the set of all subgroups of order, say if P to the power alpha was the highest power of P dividing the order of the group, then you take the collection of all subgroups of order P to the power alpha and you get G to act on it by conjugation. And then you're trying to prove that there's only one orbit there.
Got it.
Or you could, I mean, maybe that works, maybe it doesn't work. Then you think of some other action which might help you, right? And many of these are very natural actions. It's just that you have to think of them. It's not like I'll go through all the possible actions and find which one works.
Yeah.
But it's more like if I want to do this,
I'm
then
targeting them.
thinking about what might be a nice action and then follow it through and see that it works. That's the way.
So it's like with the purpose, we get to know a particular action is good or not.
Yeah, I mean, it's pretty much like anything when you want to solve a problem, you'll obviously choose the tools which will allow you to solve the problem, right?
Absolutely, ma'am. Yeah.
But the point is that we've not really been trained in group theory to start looking for group actions as a method to solve the problem. And the idea or the hope is that you'll see how powerful group actions are, and I mean, and therefore start thinking about that as a natural way to think about groups, even towards solving problems related to groups, including in research. I mean, it's not just at the levels of group theory that you're doing at the undergraduate level or even at the postgraduate level. Even when you're working on research, a lot of the time you're you're thinking of natural group actions which you can exploit, or a suitable group action that you can exploit. Okay,
Thank
so
you, ma'am.
you're welcome. You're welcome. So let's get started for today. And so I'll share my screen now. Uh, Shweta, you'll have to allow me to share screen.
Yes, ma'am. Ma'am, just check now.
Okay, so let me start with a very quick review of what we did, just the basic definitions, and then we will look at Burnside's theorem. It's an orbit counting theorem. It counts the number of orbits basically. So yesterday we talked about a group G acting on a set X. Okay, and we saw that this gave rise to a homomorphism phi from G to Sx, and this is called the permutation representation for G. And we could define for every X belonging to X something called the orbit of X or OX, and this consisted of all the points, other points in X to which little x is taken under the action of G. Okay. Another thing that we could associate was what was called this is of course a subset of X. Then we had the stabilizer of X, which we denoted as Gx. And this was the collection of all G in G such that G fixed X. And we saw that this is a subgroup of G. Further, we proved orbit stabilizer theorem. Which basically says that the cardinality of OX is the same as the cardinality of the set of left cosets of Gx in G. And when things are all finite, then we have that the number of elements in OX is nothing but order G upon order Gx. So this was what we called as the orbit stabilizer theorem. And another fact is that the orbits form, they're basically equivalence classes. So in your mind, the picture that you should have of X is that it's partitioned into these orbits. So I have OX, OY, OZ, say. Okay. And so in a finite situation, we also have that order of X is nothing but the summation. So if I have K orbits, say, I equal to 1 to K, order of OI, these are the distinct orbits. And I choose Xi as the representative in OI. Or rather, you're thinking of OI as nothing but the orbit of Xi. Then this just turns out to be summation I equal to 1 to K, order of G upon order of GXI. So these were some of the few things that we covered in the last lecture.
So ma'am, order can never be empty now? Matlab,
Orbit.
Orbit, I mean, yeah.
Orbit can never be empty. I mean, by definition, orbit is associated with one element of the set. That's how we are defining orbit in the first place. Later, we saw that it was an equivalence class, but O of X will always contain X, right? Because one, if I take one as the identity of G, then one times one acting on X is just X. So certainly, I should in fact have maybe mentioned this, that what you'll see is that since 1 times X equals X, therefore, X will always belong to the orbit of X. Okay, so orbit is never empty. But you can also think of orbit as just the equivalence class coming out of that equivalence relation where we said that X is related to Y if there's a G in G such that G dot X is Y. So you can prove that that is an equivalence relation, and the equivalence classes are nothing but your orbits. Okay. So today, as I said, I'm going to talk about, well, not the Burnside's theorem or not the Burnside lemma. So I'll tell you a little bit about, basically in 1960, this result that we are going to talk about started being called as Burnside lemma or Burnside's lemma. But it was never proved by Burnside. In fact, before 1960s, this lemma existed and it was presented in a lot of literature, and it was not given any name at that point. And if you go back further, Cauchy and Frobenius proved more generalized versions of this lemma. Okay, so actually it's one of those lemmas which has got named wrongly, but now it's known as Burnside's lemma. So what does Burnside's lemma do? It does counting. It's a tool for counting. And basically what you're asking is, suppose I'm in a finite situation. I have a finite group which is acting on a finite set X. And I know that once that action takes place, there are orbits, right? So is there a way in which I can find out how many orbits will there be under this action? And so that's basically what Burnside's lemma does. But before I tell you about Burnside's lemma, I'm going to introduce one more set. See, in above, what you saw was orbit and stabilizer are all being defined via an element of X. But this time, what we are going to do is we are going to take an element G in G and use it to define something. So again, what is the scenario that we have? So this is, I'm not yet coming to Burnside's lemma. This is still general. So let G act on a set X. I'm not writing non-empty, but the assumption is X is non-empty. Okay. Then for each G in G, we define FG. It's also called fix G. And what is fix G? It's the collection of all those X in X which are fixed by G. Okay, so that's just the definition that we have. So for example, we saw that if we take a vector space V, vector space over a field F, then F star acts on V. So this is your group G and this is your set X. Okay, and G is acting on X. Now here, suppose I wanted to, so let lambda belong to F star and I want to know, so what is fix of lambda? By definition, this is all those vectors in V such that lambda V is going to be V. Okay, and you can see what does lambda, when you look at this quantity, that is when you scalar multiply the vector by lambda, what's really happening is that your vector is just getting scaled. So if you think of your vector in R square and you're multiplying it by a real number, basically the magnitude of the vector is changing, right? Now, so think about this. When can the magnitude stay the same? That's, so that can only happen if V is 0, right? If lambda is not 1, then lambda V is going to be V only if V is 0. So what you find is that this thing turns out to be just the set 0 if lambda is not equal to 1, 1 being the identity of the field F, multiplicative identity, and it will be the whole set V if lambda is equal to 1. Okay, so that gives you an idea of what fix is. Maybe one more example. Let G act on itself by conjugation, and let little g belong to G. Okay, so we want to find out, then let's see what fix of G will be. By definition, so the G is acting on itself, right? So so by definition, this is all the X belonging to X, which here is just G, such that G dot X equals X. And remember what the action is, it's conjugation action. So this is the set of all X in G such that Gx G inverse is equal to X. Okay, so this is all those X in G such that Gx is equal to Xg. So once again, you find that this is nothing but the centralizer in G of little g. Okay, that's what fixed G is. So now let me state Burnside's lemma for you. So let G be a finite group acting on a finite non-empty set X. And let X by G denote the set of all distinct orbits under this action. Then it says that the number of orbits, which is the order, so this is the number of distinct orbits, is nothing but the average of all the fixes. So you look at each element of G, take the fix of G, sum up all those orders and average it over order of G, and the answer is going to be the number of distinct orbits. Okay, so it's a way of counting distinct orbits. And after I finish the proof, we'll see some very interesting counting places where we can use this result. I've also given you, I'm sure this would have been shared with all of you, that there is an article written by Peter Neumann on Burnside's lemma. And that actually tells you some other ways in which this Burnside's lemma occurs in group theory and in counting. Okay, so let's see how will we prove this. See, the idea is very simple. The idea is that you look at this set E, which consists of, so this is a subset of G cross X. Okay. How is it defined? This is defined as the collection of G comma X belonging to G cross X with the property that G acting on this little g acting on little x is just X. Okay. So, and the way in which you get this result is, I wanted to change the color. Anyway, the way in which you get this result is just by counting the order of E in two different ways. Okay. What do I mean by two different ways? See, so one is, so I want to know which are all the ordered pairs which are going to sit in E. So what I can do is I can say for each G in G, I count all the X's in X such that G dot X is equal to X. Okay. So in the first approach, what we'll do is we are going to fix the first coordinate and then count how many second coordinates can we have for that G. And obviously, then I sum over all the, if I sum this over all the possible G's in G, I'll get the order of E. Okay. I'm not saying that for each G there will be an X. So it could be 0 in that sense. But what we'll, as a process of counting, what we're going to do, we're going to fix the first element and then count how many choices of G comma X will we have with G as the first coordinate, which is this. And on the other hand, what I can do in the other direction is I can say, let me fix X for each X in X. I count all the G in G such that G dot X is X. Again, if I take this over all the possible choices of x I have in capital X, I'm going to get the order of E. And then when I equate these two things, I will end up getting the formula for Burnside's result, Burnside's theorem. Okay. So let's look at the first approach. So I'm writing the proof now. So let G belong to G, and let us consider all x in X such that G dot X equals X. Okay. But then if G dot X is equal to X, what does that tell us? That tells us that see, if you examine this G dot X equals X, then what you're going to get is that this is the same as saying that G belongs to, this is the same as saying that X belongs to the stabilizer of, I'm sorry, G belongs to the stabilizer of X, and this is also the same as saying that X belongs to fix of G. Okay. So this G dot X being equal to X is equivalent to saying that G belongs to the stabilizer of X and X belongs to fix of G. Okay. So if I look at E, so remember that G comma X belongs to E if and only if G dot X equals X, which is if and only if G belongs to the stabilizer of X, and again it's if and only if X belongs to the fix of G. Okay. So this is the key thing that you have to remember. And now let's do our counting. Okay. Clearly, order of E is going to be equal to summation G belonging to G, the number of elements of the set G comma X such that G dot X equals X. Okay. So remember what E consisted of? It consisted of all possible such ordered pairs. And now what I'm saying is I do this counting systematically. I first of all allow G to vary over all the elements in G. And for each such G, I'm counting how many X's are there. Okay. So in this bracket inside, my G is fixed and X is varying. Okay. So now this is obviously equal to the summation of all those G in G such that this is the order. What is this set? This is the set of all X belonging to X such that X belongs to fix of G. That's precisely the order of this is equal to the number of choices of X that I have, satisfying G dot X equals X. And that's what I've written. X belonging to F fix G is the same as writing that G dot X is X. Okay. So this is simply nothing but the order of fix G. So this is summation Therefore, order of E is nothing but sigma G belonging to G, order of fix G. So we've got one of the portions that we wanted. Fix has come into the picture. I've got it going over all possible G in G, and it is connected to order of E. Now let's do the second kind of summation that we want to. So again, order of E is going to be summation X belonging to X, order of the set G comma X, such that G dot X equals X. And here, what do we know? We know that X is fixed. Once we go inside the summation, X is fixed and G is varying. So so the set whose order I'm looking at inside is basically summation X belonging to X. And what is the set I'm looking for inside the order? This is just the collection of all G in G such that G dot X equals X, right? But this we saw is exactly the same as saying that G belongs to the stabilizer of X. So what you get is that this is nothing but summation X belonging to X, order of Gx, right? But here we can simplify things better. Now let the distinct orbits under the action be O1, which is orbit of say x1 all the way up to OK, which is the orbit of say xk. All right. So the picture that you should keep in mind is that we have the set X and we have these k orbits O1, O2, OK. And see, when we are talking about little x varying over x, instead I can count first, let me look at all the x in O1, then I can look at all the x in O2, and then I can go and look at all the x in OK. So this summation can now be broken up into further bits. So I count over this, then I count over this, and then I count over this. So I can use this to write that, therefore, now since X is the disjoint union of OI, I equal to 1 to K, therefore, I get that order of E is nothing but the summation I going from 1 to K. Again, once I fix the I, then I take X belonging to OI, order of Gx. Okay? So I have now broken down this summation that I had here, this summation that I had here, as summing over this, and then this. And I end up with this particular summation. Okay. So now the question is that how does this help us? Now the interesting thing is that if two elements belong to the same orbit, then the order of their stabilizers will be the same. Okay. So note, and I'm going to leave this as an exercise. I hope you'll take it up in the tute or otherwise try it, that if x comma y,
Excuse me, ma'am.
yeah, go ahead, ask.
Ma'am, can you please explain this step again? The
This step,
summation one.
yeah. See, so the point is that here, if you look at it, what does it say? For each little x in x, find all the gx, order gx, right? But this little x in x, because this is a partition, has to come from exactly one of these orbits, right? So when I want to count all, when I want to vary x over all the elements in capital X, I can do it systematically. I can say first, let me do this, if I want to do this counting, let me first take all the x belonging to O1 and then calculate this. To that, I take all the x in O2 and again calculate this. Then I go to O3, vary it over all the x in O3, calculating for each such x the value, and so on. Okay, so it's like so suppose I had to do. Let me give you a very quick example. Suppose I had this as x, and maybe there's just 2 orbits. Here I have x1, x2, x3, and say here I have x4 and x5. All right. So this thing is saying the first summation that I have, this is saying, let's count. It's saying order gx1 plus order gx2 plus order gx3 plus order gx4 plus order gx5, right? That's what this thing is. It's varying over all the x's in x. But instead what I'm doing is I'm counting this group first and then this group and then adding the 2. That's what I'm doing in this. Is that clear now?
Yes, ma'am. Thank you, ma'am.
Yeah. So basically you're breaking up your counting into parts. First I'll count this value of gx for all these xi's. Then I'll count it for all these. And of course, here I have k such things. So I have to count for all the x's here, then all the x's here, and then all the x's here. And that's just written in this way. Okay. Now, what I wanted to say is that if you take x and y both belonging to the same orbit, okay, remember this orbit was an equivalence class. This will happen if and only if there exists a G in G such that G dot X equals Y. And what you can show is, show that Gx and Gy will be conjugates. It's very easy to show that if you know the stabilizer of X, then the stabilizer of Y will just be the collection of all conjugates of things in Gx. Therefore, what you get is order of Gx is the same as order of Gy. And since we are taking this as orb of Xi, this will also be equal to order of Gxi. Okay. So the point is, for every x in this orbit, you have the order of this stabilizer is the same, and it's nothing but order of Gxi. Okay. So let's use this. Therefore, again, what I'm getting is order E, which I knew was summation I equal to 1 to k, summation x belonging to OI, and this GX is now for all the X in OI, it's a constant and its value is order of GXI. So when you have this particular summation here, basically what you're saying is this constant value, you're adding as many times as there are elements in order of, in this orbit OI. So this is nothing but, this thing is nothing but, again, summation I equal to 1 to k, and how many order GXIs am I adding? As many as order OI. So this is order OI into order GXI. But recall orbit stabilizer theorem. It says that order of OI is nothing but order G upon order GXI for all I. Okay. So if I utilize this therefore is, so order OI into order GXI is order G. So this is nothing but I equal to 1 to k order G, which means that this constant order G, I am adding it k times. So what I'll end up getting is that this is nothing but k times order G. But what is this k? This k is nothing but number of distinct orbits. Therefore, what we are getting is that k times order G is equal to order of E is the same as summation G belonging to G order of fix of G. Okay. Thus, we get k, which is nothing but the number of distinct orbits, is equal to 1 upon order G summation G belonging to G fix G. Okay, please remember that the number on the right hand side is also a natural number. Okay. Of course, it's possible that some of these order fixed G's might just be 0. You'll see that later in the examples that we do. But what this is saying is for each little g in G, find this collection of fixed G's, find their orders, add them all up and divide by the order of G, and that will give you the number of orbits. Now, where is this number? So any doubts that any of you have in the proof so far? Otherwise, now what we'll do is we'll look at how to use this counting theorem. Okay. So these are basically, I mean, of course, you can use it for most serious things as well. But I'm going to talk about some nice puzzles which you can solve using this thing. Okay. So here are some puzzles, counting puzzles. Okay. So basically, you have a factory or some office which is using plastic squares. Okay, so this is a square which are broken into 3 by 3 grids. Okay, this is not quite a square. I should have taken one more thing here. Let me do this correctly. So there, and then okay. So they make their I cards. So of course, this is a mathematical puzzle, okay? It may not make sense in real life, but it's fun to do the maths. Okay, so they have these square plastic cards, and how they punch two holes. So you have these 9 little squares, right? So maybe I should number them. It's not numbered in the card. I'm just numbering them for our convenience. 4, 5, 6, 7, 8, and 9. So they punch 2 holes at the center of 2 of these 9 squares. Okay. And the question is how many, and so in this grid is both front and back. Okay, so even if you turn the plastic card around, it looks exactly the same as what it looks like on top. So how many distinguishable cards can you make? I cards can you make? Now, what does this mean? See, the point is that suppose I had a plastic card where I had a hole in these 2 places. All right. Now, while I'm so if you think of this square, suppose you do a, when you're looking at the symmetries of a square, you know that you have 4 rotations and 4 reflections, right? Now the point is, suppose I reflect this about the vertical axis. Okay, just think of it. Then what will this square go to? This square will look like, if I do a vertical reflection, then this square is going to, this thing will stay as it is, but this circle will move here, right? Now the point is that I could have, while presenting my I card, just flipped it about the vertical line, right? That is, I just turn it like that, and then it'll look like this. Okay, so I cannot give one person a card which has 2 holes punched like this, and the other person a card which has, so here the punching of the hole is in the position 2 and 4. And here the punching of the hole is in position 2 and 6. Okay. So I can't, if I give this, both persons' identity card will look the same, really. The person who's checking or the machine which is checking is not going to be able to distinguish this card from this card because the numbers are not printed. 1, 2, 3, 4, 5, 6, 7, 8, 9 is not printed. It's just these holes. Okay. And depending on how you put the card into whatever is reading or how you present it to the person reading, this card and this card will look the same. In fact, if I do a 90-degree rotation of this card, then what will happen? This hole, so if you do a 90-degree rotation, this hole will come here and this one will go here. So I'll end up with position 4 and 8. That's also the same card. So the point is that any symmetry of the square that I apply to this card, all the different positions these 2 holes can go to, they're all the same as this, right? So when we ask how many distinguishable I cards you can make, basically what you want to know is how many orbits are you going to get under the action of all these plastic squares with 2 holes punched under the action of D4. Okay. So is everybody clear about what I'm saying here? So when you're asking this, in mathematically, what is happening is I have this set X, which is the set of all plastic I-cards with 2 holes punched. And how many cards? I'm no longer asking distinguishable cards. How many cards? That is, what is the order of X? It is, how do you decide what the order of X is? You have these 9 grids, 9 little squares, and you have to create a card by punching 2 holes. So it's just going to be 9 choose 2. Okay. So that is 9 into 8 upon 1 into 2. So this is 36. Okay. So you have 36 such plastic cards that you can make, but not all of them are going to be useful to you. So what you want to find how many distinguishable. Now, wishable I-cards. Okay. So here, what you have to think about is, so 2 plastic I-cards, say X and Y, are not distinguishable if and only if there exists a row belonging to D4, which is symmetries of a square, such that if I apply rho on X, I end up getting Y. Okay. So therefore, number of, so basically what we are saying is, in other words, D4 is acting on X, and the number of, so this is the same thing as saying that little x and little y belong to the same orbit. Okay. So 2 things are not distinguishable if they belong to the same orbit. So how many distinguishable cards? As many as there are orbits. So the number of distinguishable I-cards is the same as the number of orbits. And we know by the Burnside's lemma that what is this? This is equal to, remember, the number of orbits is equal to summation G belonging to D4 order of fix G. That's what it is. So now what we do is, for each element in D4, we calculate how many plastic I-cards will it fix. Okay, so that's our aim. So what are the elements of D4? We have 4 rotations. So rotation 0 degree, rotation 90 degree, rotation 180 degree, and rotation of 270 degree. Okay. Remember this symmetries of a square, and then I have a flip around the vertical. Then I have flip about the horizontal. And if I call this, say 1, 2, 3, 4, then I have the diagonal flips. So I have D F13 and I also have F24. So these are the 8 elements of D4 and I have to find out their fixes. So for R0, which is, this is nothing but identity, obviously it fixes everything. So fix of R0, R of 0 degree is clearly the whole of X. Okay, that's the first thing. Now let's try and see what it is for the 90-degree rotation. So remember, you're looking at D4 acting on these plastic cards which have 2 holes punched. All right. So the point is that because there are 2 holes punched, at least one of the outer positions is going to be punched, right? In any plastic card, definitely one of these outer positions will be punched. So I want to know which of these plastic cards with the 2 holes punched are going to be fixed by a 90-degree rotation. All right. And you'll pretty much see nothing will be fixed, right? Because there'll be at least, even if one of the holes is in the center, there has to be at least one which is outside of the center. So let me start with a hole which is outside of the center. Say that hole is here. Now, I don't know where the second hole is, but with this hole, when I do a 90-degree rotation, it will go here. Okay. But remember that I'm trying to find all those plastic cards which are fixed by the 90-degree rotation. That is, under the 90-degree rotation, so when I'm looking at fix of R 90 degree, I want all X belonging to X. So all those plastic cards, such that when I apply the 90-degree rotation on X, it actually takes it back to X itself. No longer looking like X, but it has to take it back to X itself. So the point is, if I do a 90-degree rotation, then this point is going to move here. All right. And the only way the plastic card would look exactly as it did when only way R 90 degree therefore would preserve X is if this was the second hole. Okay, so starting from assuming that one of the holes must be somewhere on the outside and knowing that this card is fixed by the 90-degree rotation, I conclude that basically wherever this hole goes to under the 90-degree rotation, that is where the second hole has to be. So the second hole is somewhere here. All right. But now we have a problem, right? Because now my plastic card looks like this. But if I do a 90-degree rotation, then what will happen? This hole moves here, but this hole will move here. Okay. So the new card, so what happens after I do 90-degree rotation is, this was in position 2 and 4. Okay. After I do the 90-degree rotation, what happens is, this goes here, this goes here. And this is position 4, 5, 6, 7, 8. Okay, so it's not being fixed. All right. So this argument is showing you that whichever plastic card you pick, it is not going to be fixed by R 90 degree. Okay. So this is definitely not equal. This was our X we started out with, and this is definitely not equal to X. Okay. Therefore, no plastic card, I card, will be fixed by R 90 degree. Okay. So this argument is showing you that whichever plastic card you pick, it is not going to be fixed by R 90 degree. Okay. So this argument is showing you that whichever plastic card you pick, it is not going to be fixed by R 90 degree. Okay. Therefore, no plastic card is fixed by the 90-degree rotation. Okay. Therefore, fix of 90-degree is 0. I mean, order. And you can check that since R 270-degree equals R 90-degree inverse in the group, therefore, I mean, the order of the fix will be the same. In fact, you will find that, I mean, you can check quite easily that this will be the case. Equals 0. So 3 of the things are done. Now let me look at the 180-degree rotation. So for the 180-degree rotation, so let me give you a few minutes. So can you think of whether there'll be any plastic cards which are fixed by the 180-degree rotation? Where can you put your 2 holes, the punched holes, such that when you do a 180-degree rotation of the card, it is exactly the same card.
Second row and second
7
column.
or 3, 7 or 1, 9.
Sorry. Say that again. 3.
3 and 6, 7.
3
or
and 7.
Or 1 or 9.
First, let's take this. So if I look at a 3, 7, right? What will happen when I do a 180-degree rotation? When I do a 180-degree rotation, this position 3 will come here and this position will go there, right? So what I again get is X itself. So the person is absolutely right that when you do a 180-degree rotation and you have these punched holes in these 2 places, then you are going to get that it is fixed by the 180-degree rotation. So what are the combinations we are getting? So one is 3, 7. This is not necessarily ordered pairs. Huh? I'm just, for us, 7, 3 and 3, 7 are one and the same. Okay. So, of course, this is 1. What else? Similarly, I'll get, if I put something at position 1 and position 9, again, I should be okay, right? 1, 9. What else?
2, 8 and 4, 6.
Yeah, so the point is that if you again put something in 2 and 8 and do a 180-degree rotation, you'll find that it will come back. I mean, it will be fixed. And the other positions are this and this. So you get the 2, 8 position and you get this is 4, 5, 6, 4, 6. Okay, so these 4, so 4 plastic cards are definitely fixed. But I have 36, right? So how do you know that these are the only ones fixed? What is the argument I can make which says that this is the only one fixed? See, first of all, if the hole is in the center and one other hole is somewhere else, such a thing is not fixed by 180-degree rotation, right? Clearly, because when I do a 180-degree rotation, this will stay where it is, but this thing is going to travel here, and that is no longer the same card. It's not fixing X. That is under the orbit also, it's taking X to some other element within the same orbit. Okay, so it's not, so none of the cards which have a hole in the center are going to be in the fix of G. Apart from that, what else is left? If you forget about the positions being in one of these four cards, that means your you're going to have situations, say like this, or if you look at something like this, you can clearly see that when you do a 180-degree rotation, you'll end up with things here and here, right? So you can actually go through each one of them or have an argument which says that, actually the argument is, you can make it in a slightly better way. You can say that if you pick any, so we've already seen that you cannot have a hole in the center if you want it to be fixed by a 180-degree rotation. So both the holes have to be in the outer portions. Let's pick any one hole that is there already, say it's here. Then I know if this card is fixed by a 180-degree rotation, then when I do the 180-degree rotation on it, I will know exactly where this hole goes. It will go here. And this is the card, which is then fixed by 180-degree rotation. So for every point that I choose in these outer grids, there's exactly one other point where I can place the second hole such that the 180-degree rotation actually works. And so the point is that, and then you'll see that, therefore, I'll only get this thing 1, 9, or I'll get 3, 7, or I will get a 2, 8, or I will get a 4, 6. So these are the only 4 things that are possible and are fixed by the 180-degree rotation. So fix of the 180-degree rotation order is 4. Okay. What about the flips? So I'll do one of them. And so let's say we are looking at the horizontal flip. Okay. So I want to find out what is the fix of F horizontal.
We can also use the same argument which you used in the Burnside lemma, the counting thingy that you used.
That's what I'm aiming at. Ultimately, I'm going to get the number of orbits by counting the order of all the fixes and then dividing it by the order of G here, which is D4, which is 8. Okay, so that's how I'll get the number of orbits. But in order to calculate the number of orbits, I have to count all the fixes. So what is fix of FH here? Now I want that's the horizontal flip, right? So under this, I want all those cards X such that when I apply FH to X, I just get back X. So what are all the positions I can place things in so that it looks exactly, I mean, it is exactly the same when I do this horizontal flip.
1739.
So 1 and 7. Okay, 1, 7. Similarly,
2, 8, 3, 9. 8 and 3, 9.
3, 9. What else? You're forgetting something.
The horizontal axis.
4, 5.
Anything on the horizontal axis? Any two?
4 and 6.
4 and 6.
So I could have 4 and 5 also.
4 and 5 also, 5 and 6 also.
4 and 5,
So
5 and 6.
4 and 5.
4 and 6.
5, 6, 4, 6.
3 choices there, no? 4,
Ma'am, but since like we are taking horizontally, so like why are we considering this 4 and 5 and 5 and 6? I didn't get this part.
What will happen if you do a flip on this card? If I take a card like this and I flip it horizontally, which means I'm flipping like this. Again, the position will be 4 and 6 only, no?
Yes, ma'am.
Can you see that? I mean, it's the point is anything on the reflection axis doesn't move actually. When you do a reflection, all points on the line of reflection stay the same. So if you take any 2 points on the line of reflection, they're all going to be fixed by that reflection. This is a property of the reflection. So but of course, in my case, on the line of reflection, I'm only allowed to put, there are 3 points, which are the centers of these middle squares, and I have to choose 2 of them. And any 2 points that I choose, when I take that card, imagine a plastic card that you have, where there are these 2 holes. So my plastic card is like this, and I'm going to flip it. This is like a horizontal flip. And then you will see that the 2 holes are still in the same place, right? They're still in 4 and 6. They're not moving. I mean, the configuration that I'm going to get is not moving the 4-6 position out of the 4-6. I mean, sorry, this is 4-5 to something else. If I do a 90-degree rotation, this moves, right? If I do a 90-degree rotation to this, what will be the new position? See, this is 4-5. If I do a 90-degree rotation, it will become 5-8. Whereas if I do a horizontal flip, it still stays 4-5. If I do a vertical flip, it will become from 4-5, it will become 5-6. But in a horizontal flip, it's going to, if I start with holes in 4 and 5 position, after the flip also the holes will be in 4 and 5 position only. Okay, so how many, now I've got 3 which are, my, these points. Okay. And then 3 coming out of 2 out of these 3 choices that I have here. So what are the things we are actually getting? If I see, either I have to have this and this, or I have to have this and this, or it is this and this, or I can choose any 2 out of these 3 positions. These are the plastic cards which I can see very clearly will be fixed by the horizontal things. And that means and of course you have to check that if there are no other cards which are fixed by the horizontal flip. Now, how do you make an argument like that? Again, you'll have to just argue that, okay, let me take the position of the first hole. It could be anywhere. It could be either on this horizontal axis or off the horizontal axis. Now, if it is, say, here, then I know that under the horizontal flip, this thing goes to this position. So this is the only position in which the second hole can be, such that this card will be fixed by the horizontal flip. Similarly, if my first hole I'm assuming to be here, or alternatively here, here, or here, the same argument works. But of course, if I take my first hole lying on one of these positions here, then what I'll find is that if I put a hole here, then I can see that when I do a horizontal flip, this hole stays exactly where it is, right? So the second hole that I need to put also needs to be in a place where it goes back to itself under a horizontal flip, which means that it will either have to be put here or here. I'll have no other choices. So for a hole being here, I have 2 possibilities. And if a hole is here, then I have 2 possibilities. If I have the first hole is here, then I have 2 possibilities for the second hole. And you'll see by that argument that precisely these 6 configurations are the ones which are going to be preserved by fix of h. So the order of fix of fh is going to be 6. And you can check by a similar argument that this is exactly what you'll have for the vertical flip as well. Okay. Now, what other thing is there? There is this diagonal flip. In this, what happens? It's a very similar argument that you use. Anything on this line is going to stay where it is. So when I choose the card configurations which are going to be fixed, if the hole is here, then I have two choices. Okay, so if I look at the F13 flip, then what are the configurations that I'm going to get for the F13 flip? Can someone tell me? So again, I'll get 1. I can put this at 5,
1,
or I can put this
5,
at
9,
9,
1, 5, 1, 6,
5, 9.
5, 9.
On the other hand, suppose I start with this position, then when I do this flip about this line, then the only other place that I can put the hole so that the card stays the same is here.
2 and 4.
So yeah, you'll get 2, 4. Similarly, I'll get
3,
these two.
6,
3, 7.
3,
3, 7.
7.
3, 7. And I'll get these
6,
two.
6, 8.
6 and 8.
6, 8, yeah.
So again, I have 6 elements in the fixes of the reflections. So if I total this, now the number of orbits is going to be equal to order of fix 0 degree plus fix 180 degree. 90 and 270 I'm leaving because we know those are zeros. And I know all the 4 reflections have 6 elements in their fix. So that's 4 into 6. Okay. And a fix of R0 we saw was the whole set X, which had 36 elements. The 180 degree rotation had 4 elements, 4 cards which were fixed. And from the 4 reflections, each of them fix 6 cards. So I get 24. So the total is, so that's 36 and 4, 40.
64.
Yeah, it's 64. Okay, I have to divide it by 1 by 8.
8 is the answer.
1 by 8. So that's 8. So basically out of these 36 plastic iCards I could punch, only 8 are distinguishable. Okay, so that's what this result, this says. So I'm going to give you as an exercise. Of course, there's some in the tutorial sheet. So you have 8 beads, out of which 5 are white and 3 are black. Okay. So you have to imagine them as the beads as being, so there are total 8 beads, right? So think of D8, the octagon. So you have to think of your necklace as being the vertices of a octagon. Okay, so position 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so this is where you'll be placing your 8 beads. And again, when are 2 necklaces? So you can think of D8 acts on on the set of all necklaces. And when are two necklaces distinguishable? If they are not in the same orbit, basically. So the question is, how many, actually let me tell you the answer. Show that exactly 5 necklaces are distinguishable. Again, you're going to count orbits under the action of D8, which is the symmetries of a regular 8-gon on the set of all necklaces, which you can take as X. And how many elements will X have? See,
8 elements.
See, there are 8 positions, or in a way, I mean, out of these, see, you have 5 white beads and 3 black beads. The beads are not distinguishable. So the question is that, so it's like if you have a set of, you have to create a set of, well, let me put it this way, from those 8 positions, you have to choose the positions where your white beads will go or your black beads will go. The moment you choose the position where your black beads go, automatically the rest of the positions have to be occupied by the white beads. So the number of choices you have for where the black beads go, and again the order does not matter because the black beads are not distinguishable. So it is going to be 8 choose 3. Order of X will be 8 positions, out of which I have to choose 3. So that will be the total number of necklaces that you can make. Then D8, which is a group of order. So D8 will have how many? It has 8 rotations. And what is the angle? The smallest non-zero degree angle, the basic rotation is going to be 2 pi by 8. Okay. 2 pi by 8 is the minimum non-zero degree angle. And there'll be 8 rotations starting from the 0 degree, R2 pi by 8, then R4 pi by 8, and so on. And you'll have 8 reflections. And for each of these, you have to find the fixes. And you can pretty much quickly see that the rotations are not going to fix anything, basically. Right? Because just think of it. I mean, you have 3 black beads somewhere scattered in this in this necklace. And the moment you do any non-zero degree rotation, it's obviously going to move to I mean, basically none of these rotations are going to fix those 3 points. Whatever 3 points you choose on this configuration, none of these non-zero degree rotations are going to fix any of them. So you will not get, so apart from your 0 degree rotations, the other rotations are not going to contribute anything through their fixes. So basically you'll have to figure out in terms of your reflections what are possible. Now, what are the reflections that happen in this regular N8-gon? Either you have midpoints of opposite sides or you have diagonals. Right? These are the 2 types of lines of reflection you have. Now, if you look at something like this, see, it's basically dividing your necklace into 2 equal halves, right? But you have 3 black beads. So on one side, there'll be 2 and on the other side, there'll be 1. And when you flip about any of these lines joining midpoints of opposite sides, you're obviously not going to fix, because when you flip the black beads, say, which were 2 on one side, will go on the other side, and there'll be, then it will not obviously be the same necklace, right? Because the new one that you're getting will have 2 on the left and 1 on the right, whereas you started out with 2 on the left and 1 on the right. So you'll find that none of these will also not contribute. So basically, you just have to look at the 4 reflections that you get when you're looking at lines joining 1 and 5, or the 2 and 6, or 3 and 7, or 4 and 8. There you'll have to find out how many necklaces are being fixed. And then when you add it all up and divide by 16, you should get the answer, which is 5. Okay, so I'm giving this as an exercise because I'm kind of running out of time. In fact, I mean, I know we started a little late. So Shweta, should I stop here today, or should I do a little bit more? And or what?
You can do it tomorrow. Otherwise, they'll not get a break.
Yeah, exactly. So let me stop here, and then maybe tomorrow's thing, I will start with Cauchy's theorem, because I do want to tell you how you can prove Cauchy's theorem using group actions. And then we will move on to looking at strip patterns and so on, and some other things. I'll try and do some demos on GeoGebra. I mean, you don't have to try it yourself while I'm doing it on GeoGebra, but later on, you can download GeoGebra for your laptops or for your phones, and you can try some of the things that I'll show you in the next thing. So let me stop sharing.